Welcome to Math 2320. This is section 2.5. In this section, we make some substitutions if possible, and it transforms our equation into one that's easier to do. Now, in our first set, we're looking to see if a function is homogeneous of a particular degree. So what does that mean? What that means is the following. If we plug in tx, ty into our function, and if the output is t raised to a power times the original function. So for example, f of x and y is x squared plus y squared. If I substitute in tx, ty, then I get tx quantity squared. And you see in this point I can factor out a common t squared and I get back the original. So what this is now is t squared times f of x and y. So that would mean that it is homogeneous of degree 2. Now a function doesn't have to be homogeneous. For example, f of x and y is x cubed plus y. If I plug in tx, ty, then I get tx quantity cubed plus ty. And when I simplify that, I get t cubed, x cubed plus ty. But there's no power of t that I can get out of this that would give me back my original function. So a function doesn't have to be homogeneous. So if we look at our differential equation, so here's our differential equation, and we saw that if the partials were the same, then we could say something and we had a technique for doing that. But what if the partial of m with respect to y was not the same as the partial with respect to n with respect to x? So in this case, if m and n are both homogeneous of the same degree, then by letting y equal ux, or x equaling vy, it will make the equation separable. So again, if both m and n are homogeneous of the same degree, then we make the substitution and it turns our equation into one that is separable. Now another common situation is something called a Bernoulli differential equation. And it looks linear, except the right-hand side involves a function times a power of y. Now this n can be any real number, just not 0 or 1. Because if it's 0, that's y to the 0, and it's simply linear. And we have techniques for solving linear differential equations. And if it's 1, then you can simply take this over to the left, and you can get a new p of x by combining these two together. So as long as n is not those two, this technique will work. And that is, we let u equal y to the 1 minus n. Alright, and in this example, which turns out to be the same as question 2, we're going to illustrate this technique. So first off, I divide through by x. Alright, so I get 1 over x. I get a 1 over x here, and I'm rewriting my 1 over y squared as y to the minus 2. So what I see is y is minus, n is minus 2. U then is y to the 1 minus n, so y cubed. All right, so if u is y cubed, that means that y is the cube root of u. And so dy dx is really dy du times du dx. All right, so what is the derivative of y with respect to u? All right, well, the 1/3 comes in the front. 1/3 minus 1 is a minus 2/3. So we're going to take our differential equation. I'm going to substitute in what I know now about dy dx, this piece, and I'm going to substitute in what I know about y. All right, so here's the opening part. Here's the part with y. Y is u to the 1/3. My y to the minus 2 is u to the minus 2/3. All right, so two operations next. I'm going to multiply through by 3. All right, so that's where this 3 is coming from. I'm dividing by u to the minus 2/3. Now here on the right, these are going to cancel. U to the 1/3 over u to the minus 2/3. That's 1/3 minus a minus 2/3, which is 1/3 plus 2/3, which is 1. And so what we arrive at then is a differential equation that is linear. So my p of x is 3 over x, integral of that. I get 3 ln absolute value of x. All right, so that's e to that. Now I'm going to take the 3, push it back up on the x from our properties of logs, and I get the absolute value of x cubed. Now way up here in the beginning we divided by x, so I have to stay away from 0 for x. So we're looking at x's simply bigger than 0, and so this absolute value can go away. All right, so with that, we recognize the left-hand side is the derivative of a product. I multiply both sides by my integrating factor. All right, and so I then get u is, once I integrate this, x cubed plus c, divide through everything by x cubed. And so u is 1 plus c over x cubed, but u was y cubed. A lot of steps, a lot of details to work out as you work these kinds of problems. All right, so let's look at question 1. Question 1, we are given our differential equation. They tell us that it is homogeneous. Well, let's just see. So m is x minus y. If I put in tx, ty, I get tx minus ty. I can factor out a t. So that is t times m of x and y. So it is homogeneous of degree 1. I also need n to be homogeneous of degree 1. So plug in tx, ty. Well, it has no y's. So I get tx, and so it is t times the original. So they both are homogeneous of the same degree. All right, so I let y be ux. Its differential using a product rule looks like the following. All right, so x minus y. I'm coming back to the original. So here's the original here. I'm now plugging in things for y, this substitution. All right. So when I do that, notice this minus ux dx cancels this ux dx. And so what I end up with then is this situation, and I can isolate the x's and u's on opposite sides. So I divide by minus x squared. This is an easy integral, so minus ln absolute value of x plus c is u. But what was u? U is y over x, right? Back up to here. U is y over x. So multiplying through by x, I get y is minus x ln absolute value of x plus cx. And to make it look like the answer that they got, I simply moved this minus x term to the left. All right, and question 2 is exactly the Bernoulli problem that we worked above. I didn't see that when I was making the notes. All right, so let's take a look here. At question 3, they tell us it's Bernoulli. Now, when you first see this, you might be tempted just to dive into it, but the problem is, remember, for Bernoulli, I needed a P of t times y. So actually, this piece needs to come to the left, and that piece needs to go to the right. So once I do that, yes, this does look like Bernoulli, where n is 2. I divide through by t squared, and so that gives us our format. So my substitution is u equals y to the 1 minus n, so 1 minus 2, or u is y to the minus 1, or y is 1 over u, which is u to the minus 1. So the derivative of y with respect to u then is minus 1 in the front, drop this by 1, and so I get minus 1 over u squared. All right, so dy dt is dy du, du dt. All right, that's going to fill in for this piece in the front. And now each of these y's I have to fill in as 1 over u. So once we do that, this is the format that we get. Now we need to clean it up. Multiply through by minus 1. Multiply through by u squared. U squared over u is u. And I multiply through by u squared. This one cancels. And I'm down to a differential equation again that is linear. So P of t is 1 over t. Integral of this is ln of t. So e to the ln absolute value of t. But again, we're considering this for t's bigger than 0. Can't have 0. So that just gives me t. So the left-hand side is using that as my integrating factor. I can recognize the left as a derivative of a product. T times the right, the t's cancel. I get an easy answer. And so plugging everything back in, dividing by t, I get to here, but u was 1 over y. And so I'm putting that together. And so 1 over y is ln of t plus c over t. And I get that y of t, flipping everything over, is this. Now, when you put this into WebAssign, it will accept that as the correct answer. But if you go back up to the printed solution, Here is the suggested answer that WebAssign gives when it writes out the solutions, which looks very different from the thing we just got. So how did they get from the correct answer to something extremely strange? All right, well, let's see. First off, if you take y over t is this. What was this? This came from back up here. I just simply divided by t. All right, so now flip everything over. All right, and then the assumption is, well, this is a constant. So I can just write this constant as ln of c, and then recognize that this is a product. All right, well, if that's a product, I can pull it back together. And now take e of both sides, and we do get their strange answer. Why did they do this? I have absolutely no clue. But the answer we got will be accepted by WebAssign. If you plugged in the problem into Wolfram Alpha and solved it that way, it would also give you this particular solution. All right, and in question 4, we're looking at something from population dynamics. All right, so first off, multiply in the p, and we get this. To make it look like a Bernoulli, I'm going to move the AP to the left. And so you can see then I do have a power of 2. So n is 2. The normal substitution is u equals y to the 1 minus n. So that's p to the 1 minus 2, which is negative 1. Or p is 1 over u. So the derivative of this with respect to u then is minus 1 over u squared. And plugging things into this equation now. All right, we're to here. Multiplying again through by negative 1. Multiplying through by u squared. We get something that is completely linear. All right, so my integrating factor is e to the integral of this piece. And so I get e to the at. Multiplying through by that integrating factor. The left-hand side is the derivative of a product. Here's e to the at times the right. Integrating this, I pick up a 1 over a plus c. And finally dividing by e to the at all the way through. I get u is b over a plus c over e to the at. All right, so c over this e to the at is c e to the minus at. All right, now at this point, I'm going to get a common denominator, multiplying top and bottom by a and pulling it together. That's because u is 1 over p, and I need to flip this thing over. And when I flip it over, I get that p of t is a over this particular solution. So what would this say in population dynamics? It would say that the limit as t goes to infinity of p of t, this term will go to 0. And so it reaches a carrying capacity of a over b.